So we want an equation like this here. So what we do is that we multiply both these sides by pi. That is, I'll multiply pi here and pi here. Instead of r, tau is equal to a sine theta into BIL. So this particular equation will give you what is the magnetic field along the axial point of a current carrying circular loop. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And today we will be looking at what happens when you place a current carrying loop in between two magnets. That is, what happens when you place a current carrying loop in a uniform magnetic field, and what exactly is a magnetic dipole. So let's dive right into it. So the first topic is torque on a current carrying loop. That is, imagine that you have two magnets like this. There is a north pole and at the other end you have a south pole, which means that the magnetic field lines will be traveling from the north pole to the south pole. So this will be the direction of the magnetic field lines, and for the time being, let's assume that these field lines are uniform in nature, which means the direction of the magnetic field vector B is in this particular direction. Now, imagine that I have a loop. Let's say I have a rectangular loop which is made up of any conductor you like. So, imagine that there is I amount of current flowing through this particular conductor. So, there is a magnetic field like this, and there is a conductor which carries an I amount of current like this. Now we are going to study what happens when you place this current carrying conductor, this current carrying loop into this magnetic field. So what do you think will happen? We know that, we already saw that what will happen to a straight current carrying conductor when it is kept in a uniform magnetic field. That is, when you keep a straight current carrying conductor in a uniform magnetic field, it will experience a force. Now the only difference is that that particular conductor is being made into a loop. Now what will this particular loop experience in that particular magnetic field? So let's take a look. So imagine that you have a current carrying loop just like this kept in between magnetic field lines. That is, uniform magnetic field lines are in between the north and south poles of this particular magnet. And let's say this particular current carrying loop is placed in between those two magnets. That means that this particular loop will be experiencing a force. And how do we find out the force? We find it using the left hand rule. So what does the left hand rule say? The left hand rule says that if you keep all the three fingers of your left hand perpendicular to each other, then the thumb will give you the force, the index finger will give you the magnetic field, and the middle finger will give you the current. If you have a hard time remembering that, you can remember it like father being force, mother being magnetic field, child being current. Just so you remember that. Let's say this particular current carrying loop has a length of L. So this side AC has a length of L. Now what I'm going to ask you to do is that find out what direction the forces are exerting on it. So in order to find that out, we use left hand rule. So right now we know that this index finger will give you the magnetic field lines. So the direction of the magnetic field lines are from north to south, which means that the index finger should be pointing in this particular direction. And now the second thing is that the current. Now we know that for the particular part, that is AC, the current is flowing upwards, which means that this is the direction of the electric current. So if this is the magnetic field, we can say that the middle finger, which will give you the direction of the current, should be pointed upwards. So basically, magnetic field is in that direction, current is flowing up, which means the thumb will give you the direction of the force. In this particular case, the thumb is pointing inwards. So you can say that the force is being driven inwards. It is in this particular direction that the force is being exerted. So this will give you the direction of the force. The left hand rule will give you the direction of the force. And similarly, if you take B and D, that is the length BD, that is also L, you can say that the direction of the magnetic field is again in that particular direction, and the direction of electric current is downwards, which means the thumb will give you the direction of the force, and that is in this particular direction. So you can actually say that if this is one direction of force, this is the other direction of force. So basically in 2 dimensions, this is the best I can show you, but just imagine that in your head that one force is coming at you while the other force is going away from you. So they are acting opposite in direction. Now we considered a current loop and kept it in a magnetic field. Now we know that there is a force being exerted on that and we know the direction of that particular force, but how do we quantitatively find that? So for that, we have an equation which we already studied, that is, what will be the force experienced by a current carrying conductor kept in a uniform magnetic field, and that equation is given by F is equal to I into L cross B. So L will be any length element which we are taking. In this particular case, if this is the length element, I can say this is DL, vector DL, then the direction of that particular DL element will be in this particular direction. So basically L is the length element which we are considering and B is just the magnetic field that. So we can say that I into L cross B will be equal to ILB sine theta, since this is a cross product, which means that the sine of the angle between the length element and the magnetic field is being considered here. This is the general equation in order to find out what is the force experienced for this particular current loop. So anyways, now this is pretty much general. We don't know exactly what we are finding out. So what we are going to do is that we are going to calculate what is the force experienced in each of these sections, because since this is a loop and this particular equation is to find out what is the force experienced for a conductor, that is a straight line conductor kept in a magnetic field, we have to calculate this individually, this individually, this individually, and this individually. All this is for a reason, trust me. So basically, when we calculate, let's say FAC, let's say the force experienced in this particular area, in this particular region, that is between A and C, we can say that it is I into the length of that wire is taken as L. So I into L into B into sine 90. Why sine 90? Because we know that the length element is in this particular direction and the magnetic field is in this particular direction, which means that the angle between the length element and the magnetic field is at 90 degrees, which means that ILB sine 90 is simply equal to ILB. You will experience maximum force in this particular case. Now, what will happen if we are taking the area A to B? So, let's say we are taking FAB. Then I can use the same equation again. I can say that I into L into B sine 0. Why sine 0? Because the magnetic field and the length element, both, if I take a small element dl here, that dl is in the same direction as the magnetic field, which means they are parallel to each other, which means the angle between them is simply 0. And again, we can write it as ILB into 0, which implies it is 0, which implies it is simply 0. So I can say that the force experienced in this particular part is maximum and the force experienced here is simply 0, which means A to C will have maximum force experienced and there will be a force experienced B to D also. But there won't be any force experienced between the lengths, that is A to B and C to D. Since these two are parallel to the magnetic fields, there won't be any force being exerted on these two parts, but these two parts will experience a force. And just now we figured out how to find out the direction of those. So we can simply say that FAC, which is equal to FBD, which is equal to BIL, since sine 90 is again 0, and FCD is equal to 0 because the angle between them is 0. So since now we find out what is the force, that is what is the exact force experienced by each of this length, I'm going to remind you of something, that is the very same heading, torque. So what exactly is torque? Torque is the couple of force, or we can simply say that when there is a force experienced in one direction and the same amount of force in the other direction, which are at different points, that is, one force is being in this direction and the other force being in the other direction, kept at a distance, then that particular object will rotate. So basically, force experienced in the rotational sense can be told to be torque. In this particular case, even though the forces are acting opposite to each other, they are acting at a distance. That is, so when this particular current loop is kept like this, it experiences a force. So basically what happens is that since there is no force experienced in the top and the bottom part, and there is only force being experienced in the sides, that is AC and BD, and the forces are in opposite direction, we can say that the forces are being exerted like this. So one force in this direction and one force in this direction, which means that one force is trying to pull like this while the other force is trying to push like this, which means so the entire thing tries to flip. So how long do you think it will try to flip? Since everything in the universe tries to have a minimal state of energy, this rotation will try to happen until the forces are aligned. That is, this force will try to go here and this will go here. That is, the object will try to spin. So that this distance decreases and decreases until the lines of forces are like this. That is, this particular coil, take this particular coil and make it 3D inside your head. So what will happen is that this particular coil will try to go for a spin. It will, since one force is in this direction and one force is in the opposite direction, they will spin. The side will spin slowly until it is like this. That is, the forces are aligned in such a manner that they cancel each other out. So that is, the torque will be 0. So when the torque is 0, do you think it will stop right there? Not exactly, because there is one more thing in effect here, that is inertia. So basically, when this flips over, the torque becomes essentially 0, but inertia still plays here. Because of that movement of inertia, it flips a little more and this torque reverses, which means that the forces reverse and this starts to rotate in the other direction. And it just keeps on rotating and rotating and rotating. This is basically the theory behind DC motors. But for now, let's concentrate more on this particular theory, that is the torque experience for a current loop. So what will happen? It will experience a force on either sides, but the forces are separated by a distance. That is, there are a couple of forces and they will produce a torque. And our job is to find out what exactly is the magnitude of that particular torque experience. So since the forces are acting in opposite direction, there is essentially no net force being experienced, but there still is torque being experienced. And we know that the equation to find out torque is tau is equal to R cross F. That is, perpendicular arm distance cross the force experienced. So we can say that this particular equation will become R cross, we already find out what is the force being experienced on both these sides. It's simply BIL. So it is R cross BIL. So now the point is, what is R? That is, what is the perpendicular arms distance? So basically, what do you mean by perpendicular arm distance? That is, if the forces are acting so and so, then this particular distance, that is, This particular distance is called as the perpendicular arm distance. So this is the perpendicular arm distance between the two forces, and that is the factor we have to find out here. The way it is done in your textbook is slightly complicated. That it is the right method actually. If it is kept in an arbitrary angle theta, that is the right manner to find that, but it's a bit of a long method. So we can use a simpler method. We assume that this particular length, that is this particular length is A. Simply speaking, this particular length, that is this particular length is A, which means that the length of axis of rotation is taken as A. The length of axis of rotation is taken as A. This particular side is A cos theta and this particular side is A sin theta. So we know that the perpendicular arm distance is nothing but A sin theta. So then we can directly write that instead of R, tau is equal to A sin theta into BIL. Now I'm going to slightly rewrite this. I'm going to write it as BIL A sin theta. Now we have a L and a A. That is, L is the length and A is the breadth. So we can say that L into A is nothing but area. That is, L is length and A is the breadth. So we can say L into A is capital A, which is nothing but area of that particular rectangular loop. So we can simply say that BIA sin theta. And here is the new factor that I'm going to introduce you to, that is the magnetic moment of this particular equation, that is I into A. So we have a new quantity that is known as magnetic moment. That is current times area will give you, that is IA is known as magnetic moment M. Just bear with me. In the next chapter, I'll explain what exactly magnetic moment actually is. For now, just know that I into A is simply M, which is magnetic moment. We have several terms in physics like moment of inertia, moment of force. Just like that, there is another term that is magnetic moment. So we can write this IA as M. So simply we can write tau is equal to MB sin theta. So basically there will be a magnetic moment that will be acting in this particular direction. So we can say that MB sin theta will be the net torque experienced by this particular current carrying loop. Then we can actually say that since M and B both are vector quantities, that is magnetic moment is also a vector quantity and vector field, that is magnetic field, is also a vector quantity. That means that MB sin theta can be written as M cross B, that is vector M cross vector B. So the net torque experienced here will be equal to M cross B, or simply MB sin theta. If you have a rectangular loop which is carrying current and you're placing it in between two magnets, it will experience a torque which will actually make it to spin. That is the theory behind DC motors, but yeah. And if you want to know what is that particular torque being experienced, you can find it using this particular equation. And one more thing you can remember is that this particular equation, that is M cross B, slightly resembles one equation in electrostatics, that is P cross E. We find out what was the torque experienced by a dipole kept in a uniform electric field, and we found out that it was P cross E or PE sin theta. Just like that, here also it is slightly similar. Here it is M cross B. There it was P cross E, but here it is M cross B. So they have a slight similarity between them, just something you can remember by. And one more thing to remember is that this is for a single loop. That is, there is only one loop placed here. If there are multiple loops being placed here, you just have to add n number of turns to the equation. That is, here it is BIA sine theta. This is just for one turn. And if there are n number of turns, you just add another n here. Then you have NBIA sine theta. That is n number of turns are there, or simply NBM sine theta. If there are n number of turns, that is there is not only one but 2, 3 up to n number of turns, you can simply say that it is not just MB sine theta. Since there are n number of turns, I can simply write it as NMB sine theta. That is the only difference that is arising here. So in a nutshell, what we did was we considered two magnets, that is North Pole and South Pole, and we considered a current carrying loop placed in between those two magnets which had I amount of current flowing through them. Since it is a current carrying conductor, we know that it will experience a force, and since it is a current carrying conductor placed in a magnetic field, we know that this particular section, which is having a length of L, will experience a force of BIL, or simply B into I into L cross B. So we found out that F, or the force being experienced, was equal to I into L cross B. And then we found out that the angle between L and B was simply 90 degrees for these two sides, and we concluded that the force will be experienced maximum on those two sides, with the only difference being the forces are acting in opposite directions. And finally, we concluded that these two sides won't be experiencing any force, which means that this particular current loop being placed here will experience a torque which will make it to spin. So basically, our next job was to find out what was the torque. So in order to find out the torque, it was R cross F. So we needed to find out what R exactly was. The only information we had was the forces acting like this, and we needed to find out what was the perpendicular arms distance, that is R. The only thing we knew was this particular angle was theta, and we then took this particular length as A. Then we could say that this side, that is R, will be A sine theta, and the adjacent side will be A cos theta. While resolving this, then we can simply say that instead of R, we can choose A sine theta. So we can simply write it. Then we can simply write, instead of R, we can write A sine theta into the force which is BIL. Here there is no sine theta because this sine theta is 1, because the angle between them is 90 degrees. So we can write A sine theta BIL. That was written as BIL A sine theta, and we know that L into A is nothing but area of that particular loop. So we wrote it as BI A sine theta, and we know that now I into A is nothing but magnetic moment. So we wrote it as MB sine theta, or simply we rewrote it as M cross B, and that is the torque being experienced by a single current loop being placed here. If there are n number of turns, we just add one n here, and then we will get the torque experienced by a current loop having n number of turns. And we also found out that this was very similar to the equation P cross E, which we did in electrostatics, and that is all about torque experienced by a current carrying loop in a uniform magnetic field. And this very principle is being used for the DC motor, just if you're wondering about applications. And we will study about generators and their applications down the road. But for now, let's see something else. That is circular current loop as a magnetic dipole. That is simply, what do you mean by a dipole? Dipole means that it has two poles. That is a north and south pole. We have only traditionally seen this in, let's say, bar magnets or horseshoe magnets, that is one north and one south. But we never really discussed about the fact that a circular current carrying loop will also have a north and south pole. I previously briefed that this will be the case, but how exactly that happens was not discussed. So we know that the circular current carrying loop will have a magnetic field similar to this. This will be the nature of the magnetic field experienced by a circular current carrying loop. Now we are going to express how we can predict or how we can quantitatively measure the magnetic field experienced by this particular current carrying loop. It is slightly an extension of the derivation we did earlier, so I'm not going to stress too much on it, but just know that there will be magnetic dipole, that is north and south pole, and that will depend on the direction of the current flow. That is, if the current is flowing in clockwise direction, we can say that it is south pole. If it is flowing in the anti-clockwise direction, we can say that that particular side is north pole. But yeah, that will be discussed in depth in the other chapters. So here for now, we'll be concentrating on the derivation. So if you remember the derivation we did, we considered a current carrying loop, that is, we considered a current carrying loop which had a radius of r. Then we considered a point P, that is, we considered a point P which was x distance away from the center of that particular loop. Then we found out what was the net magnetic field experienced in that particular point. In that particular point, using Biot-Savart's law, and we arrived at the conclusion that B was equal to mu naught I r square divided by 2 into x square plus r square whole raised to 3 by 2. This was our initial conclusion. Now what I'm trying to ask you is that if this particular radius element is really small, what will be the magnetic field experience along this center line or along the axial point? That is what we are actually going to prove here. Since that is what we are trying to prove here, we don't want to consider any element which has an r in it in the denominator term. So we can simply say that if r is very less than x, that is, x is a very large distance, so much so that this r is irrelevant, then we can actually say that the equation for magnetic field, that is B vector, can be written as mu naught I r square divided by 2 into x square whole raised to 3 by 2. Because this r square term is very small, that is approximately it will be 0. Then we can write it as such. So this 2 and this 2 will cancel each other out. Then we can write this particular equation as mu naught I r square divided by 2x cube. Whenever you see this equation, I want you to remember that this particular quantity, that is mu naught by 4 pi, was discussed earlier. This is similar to 1 by 4 pi epsilon naught. This is a constant allowed by the magnetism chapter. So we want an equation like this here. So what we do is that we multiply both these sides by pi. That is, I'll multiply pi here and pi here, which means I can simply write mu naught I r square pi divided by 2 pi x cube. Since I am multiplying the numerator and denominator by pi, there is no harm done. So this particular quantity, that is pi r square. Pi r square is nothing but area of that particular loop. So we can write it as mu naught I area of that particular loop divided by 2 pi x cube. So now we have mu naught IA. We just saw that I into A is nothing but magnetic moment. You can write mu naught into M divided by 2 pi x cube. Again, the slight problem here is that the denominator, it is 2 pi, but we need 4 pi, which means we again have to multiply this particular equation with 2 by 2. So I'm going to write this particular equation here, that is mu naught I into A divided by 2 pi x cube. I'm going to multiply both denominator and numerator by 2, that is 2 by 2. This particular equation now can be written as mu naught into I into A is nothing but the magnetic moment, which is M. So mu naught into M into 2 divided by 2 pi into 2 is nothing but 4 pi. So 4 pi into x cube. So this is the final equation. So I'm going to rewrite it slightly so that it looks better. So I'm going to write it as B is equal to mu naught divided by 4 pi into 2m divided by x cube. So this particular equation will give you what is the magnetic field along the axial point of a current carrying circular loop. Will behave as if it has two poles. That is, exactly the physics behind this is that the thing you have to understand here is that if there is a current carrying loop like this and the current is flowing this particular direction, it means that there will be a magnetic field like this. Imagine the case of a solenoid, but here it is only one singular loop, which means that the magnetic field lines will be like this. All these field lines are going like this. So let's say this is the nature of the field lines. The magnetic field lines will be experienced like this around a current carrying circular loop. But at the very center, as we move towards the center, the field lines will act like it is straightening out. So at the very center, it will be like a straight line. This will be the nature of the current carrying circular loop if we draw out the magnetic field lines. So these two sides will act as the north and south pole depending on where the direction of current flow is. If it is generally in the clockwise direction, we can say that that side or that the portion which has the clockwise direction of current flow is considered to be south pole, and where the current flows in the anti-clockwise direction, we can say that is the north pole. Generally, that is how we say that. I'll explain this in detail in the coming chapters and in the class. Now, what we tried to find out was that if this particular current carrying loop is kept like this, what will be this particular magnetic field along this diagonal or this axis? So, what will be the magnetic field experienced along this center axis? That is what we were trying to find out. So, basically what we did was, if this was the center point, then we assume that the point P was really far away from the center, so that this particular distance need not be considered. So it was approximated to 0. And then we found out what was the magnetic field experienced at this particular point, let's say P. So we tried to find out what was the magnetic field experienced in that particular point. And then we modified the equation we got from using Biot-Savart's law for a current carrying loop, and then we found out the exact magnetic field experienced in that particular point, and we wrote it in terms of magnetic moment. So basically what we just tried here to prove is that since there are two poles here, that is one north pole and one south pole, this is basically a dipole. In the case of magnets, this is a dipole. And we found out what was the magnetic field experienced at a particular distance away from this particular magnetic dipole. If you remember, in the case of electrostatics, we did a similar thing. We considered an electric dipole which is plus q and minus q separated by a small distance of 2a. We found out what was the electric field experienced at a particular distance away from that particular dipole, and we got the result as, that is, for the electric dipole, we got the result to be 1 by 4 pi epsilon naught This is the constant K. So 1 by 4 pi epsilon naught into 2p by r cube. This was the result we got in the case of an electric dipole. And in the case of a magnetic dipole, the result we obtained was B is equal to mu naught divided by 4 pi into 2m divided by x cube. X and r are simply the distance from the center. So we can say that both of these fields, as we move away from the center, falls off really steeply. That is, here it falls as r cube, here also it falls as x cube. X and r are the distances, and here both are constants, and here it is 2m and here it is 2p. This is electric dipole, this is magnetic dipole moment. So these electrostatics equations and the magnetism part are very similar in nature. Both has its own similarities since they are usually perpendicular fields, that is, they are electromagnetic fields often seen together in pairs. So we can say that for a magnetic dipole, that is, if a current carrying loop is present, which means it has two poles, north and south pole, if we want to find out what is the magnetic field experienced at a particular point away from this magnetic dipole, we can use the derivation which we just did and the considerations we just took, and we can find out what is the magnetic field experienced at a particular point. And that is the particular equation written here. So it's fairly a simple derivation, and both of these derivations are fairly simple. I hope you have understood about that. The very basic principle about DC motor and how to find out the magnetic field at a given distance away from a dipole, that is a magnetic dipole, and I hope you have no doubts. If you do, please reach out. Thank you.